So one of the things we haven't talked about yet about gases is what happens when we mix gases together. And we're assuming they're not going to do any sort of reaction. But like, for example, air. Air is a mixture of gases and they're not reacting. And so like, how do we treat that in terms of what are the properties and what's like the pressure? How do we determine the pressure when we have a mixture of gases? And so one of the first things we're going to do, as we have been this entire chapter, is we're going to assume that all the gases in the mixture are ideal. And because of that, they all behave the same. And so we only care about the moles of them. It's possible that in a mixture, all the moles of the gas of each individual gas are the same, but that's not always going to be the case. And so the total pressure, when we put all those gases together in a container, we can know the total pressure because it is the sum of the partial pressures. Now, what does that partial pressure mean? That's the pressure of the gas by itself. And this is something known as Dalton's law of partial pressures. And it basically just means, and let's take air, for example. Air pressure is the sum of the pressure nitrogen exerts, plus the pressure oxygen exerts, plus the pressure of the water vapor that's in the air, plus the pressure of carbon dioxide that's in the air, plus whatever gases, whatever minor, super minor components of gases there are in the atmosphere. And so the total pressure of a gas is equal to the sum of the partial pressures of each component, however many there are. If there's only two, then we only add two numbers. If there's 10, we add all 10 numbers together. And so let's look at a quick example of this. And the calculations and the math is pretty simple on this. We have a container that contains oxygen gas and nitrogen gas. If the partial pressure of oxygen is 0.12 atmospheres, and the total pressure is 0.80 atmospheres, what is the partial pressure of nitrogen? So when you use Dalton's law, that basically says the total pressure of this mixture is the sum of the pressure of oxygen plus the pressure of nitrogen. And so I want to know what the pressure of nitrogen is. So I'll rearrange this to solve for that. So total minus pressure of oxygen. And the total pressure is 0.80 atmospheres. Partial pressure of oxygen is 0.12 atmospheres. And so that comes out to 0.68 atmospheres. It's important to note that in a mixture, it's not always true that you have the partial pressures are equal as the gas. It's not like, oh, if I have three gases in a mixture, then they're each contributing a third. That's not the case. And very rarely is that actually true because that is dependent upon the amount of gas that is there. Okay, think about, if you have one, I'm going to kind of go extreme here. Let's say you have one molecule of gas A and 100 molecules of gas B and you put them together. What's going to exert more pressure? Well, the one that you have more molecules of. And this leads me to the second thing I want to talk about with mixtures of gases, and this is something known as mole fractions and the relationship to partial pressure. Now, what mole fraction is we use the letter X here. It's the pressure, the way we calculate it is it's the moles of that gas divided by the total moles. So let's say I have a container with two gases in it, A and B. The mole fraction of A is going to be how many moles I have of that gas over the total moles. Okay, and I find that by adding up A and B. And the mole fraction of B is how many moles of B I have divided by the total moles. And here's the thing you can always check your answer with. If I have a mixture that's just two gases, the mole fractions of each should add up to 1. If I have three gases, A, B, and C, then the mole fractions of A, B, and C should all add up to 1. Now, how does this relate to partial pressure? Because we know the amount of gas determines the pressure. The more gas there is, the more pressure there is. The less gas there is, the less pressure is. And so the relationship between mole fraction and partial pressure is that the partial pressure of A is equal to its mole fraction times the total pressure. And so the partial pressure of B is the mole fraction of B times the total pressure. So let's put this into practice. So we have a container that has 1 mole of hydrogen, 2 moles of nitrogen, and 3 moles of helium. If the total pressure is 2.60 atmospheres, what is the partial pressure of each gas? Okay, so all we have to do, let's write out take each gas individually. The pressure of hydrogen is going to be the mole fraction of hydrogen times the total pressure. The pressure of nitrogen is going to be the mole fraction of nitrogen times the total pressure. And the partial pressure of helium is going to be the mole fraction of helium times the total pressure. Now I have the total pressure here. How do I find the one thing I'm not given directly is the mole fraction. So I need to find the mole fraction first for each of these. So let's do this for hydrogen. So the mole fraction of hydrogen is equal to the moles of hydrogen. Well, I got 1 mole of hydrogen here, divided by the total moles. Well, what is my total? 1 plus 2 plus 3. All right, that comes out to 0.167 as my mole fraction. Mole fraction is unitless because it's just part over whole, and so the units cancel out. So now I can plug this in. 0.167 times the total pressure, which is 2.60. And so that comes out to point, hang on, I think I did my math wrong. Let me put this into my calculator real quick. 2 times 0.334 atmospheres. Point 167 times 2.6. Nope, sorry. 0.434 atmospheres. Okay, so now let's move on to nitrogen. Again, I'm going to find the mole fraction of nitrogen. So that's 1 mole. Actually, no, I'm sorry. We have 2 moles of nitrogen over the total moles, which is 6. So that is 0.333. So the partial pressure of nitrogen is its mole fraction times the total pressure. And that comes out to 0.867 atmospheres. And let's do this for helium. So the mole fraction of helium, we have 3 moles of it, and we have 6 moles total. So that is 0.5 moles, or I'm sorry, not moles. The mole fraction is 0.5. And so we'll plug this in. And that comes out to 1.30 atmospheres. So there's the partial pressures. And in fact, if you want to check your answer with something like this, if you add up the partial pressures, it should come out to very, very close, maybe with like within a rounding error of your total pressure. So if you add all these up, it comes out to about 2.6 or 2.60 atmospheres, which is what our total pressure was.